Okay, so that's what this is. Alpha is just change in length for unit length of the object per Kelvin change in temperature. Okay, so this is constant for a given material. So now, since length is changing, the area also gonna change, and since area depends on length times length or length times width, what happens? It picks up 2 times that alpha. And similarly, if we talk in terms of volume, then it's going to be 3 times alpha, okay? Because volume is product of 3 side lengths. So we can write like that. And sometimes this is also written as a beta, okay? But anyway, we're going to be just using this here. So this problem here uses 2 concepts. One concept, it's a concept of elasticity. It's like a Hooke's law. Remember Hooke's law? F is negative K times change in length, right? But what happens is Hooke's law is for a spring. If we are talking about rods, something like that, what happens is the area also matters. So rather than just writing in terms of force, we can write force over area kind of situation, okay? And we can look at how length is changing. So when we do that, we can write slightly different equation. Oh, looks like I haven't written that equation. So in that case, what happens is we can write generalized Hooke's law. That's called F over A is equal to Y and delta L over L. So this is like a spring constant K, but since this is not for a string but for the rods, we call that Young's modulus, and we denote that by Y. So it's a constant, right? And that number is given. So now what it says is an iron bridge is constant between 2 rock faces. So let's suppose there is no room for expansion. Then what's going to happen when it tries to expand? So for example, let's suppose if you hold a spring between two hands, compressed springs between two hands, what happens? You experience that force, push, right? So same idea here. So the bridges, they have iron rods going from one side to another side. So when temperature changes, length tries to expand. But if there is no room, there's gonna be this force built up, and that we can also write in terms of force over area, and that's what this stress is. Okay. And now, in this case, it says, you know, like temperature goes from 22 degrees Celsius to 42 degrees Celsius. So change in temperature in Kelvin versus Celsius, they are same. Temperature themselves are not same, but the change is going to be same. So although we want change in temperature in Kelvin, but change in temperature, for example, in this case is 42 minus 22 means, looks like it's exactly 22 degrees Celsius, and that is equal to 20 Kelvin. Okay, so change is same, although the temperatures are not same. For example, if you want temperature in Kelvin from temperature from Celsius, you need to add this number 273. So when you take the difference, what happens is this factor cancels out. Okay, so change remains same. So if you like, you can change this to Kelvin, and similarly this one also to Kelvin, and take the difference between two numbers and you'll get the exact same number here. So that's what we know, and it's asking us how much stress is developed. So the stress is what? So to find that, we need this. And Y is given. So Y is given. So that means we need somehow this delta L over L. Now, how do we do that? Since we know there is temperature difference is given, and we know temperature difference, original length and change in length, they are related. Change in length is alpha times length times change in temperature, right? We wrote this formula in last slide, so we can use that. And we are looking for delta L over L, so I can just bring this L down here and write like that, and it's going to be alpha times delta T. Hey, so that means stress F over A is going to be equal to Y times delta L over L, which is same as alpha times D. Sorry, alpha times delta T. So now we know gamma, we know alpha, and delta T is given. So gamma and alpha, if you don't know it, but if you know the material, let's say if it says iron, you can look for it, okay? And alpha for iron, we just wrote in the last slide. It was 12 times 10 to the power negative 6, right? So you can include all those numbers. Yes, it's going to be a bit larger number, but we have all the numbers, and that's what the calculator does magic. Okay, so that's that. And the unit of this quantity going to be, unit of force is Newton, and unit of area is meter square, because area is length times length, or length times width. So that's why you get Newton over square meter. So that's how you can use it. So that's how length changes, length of the object change. So it's not just the length, the area change, volume change. So fluid inside our body, if our body were to, body temperature were to change, the fluid inside our body is going to expand. Fortunately, our body has this mechanism of keeping temperature constant, right? So our temperature, body temperature remains same. Yes, when we have a fever, temperature goes a little bit higher, but it's not going to change the volume by much. So we are still fine, okay? But let's say if you try to boil something, by filling your pot all the way to the brim, what's going to happen? If you heat, temperature going to start increasing, and the volume of this thing going to increase, and it's going to start spilling up, okay, even before boiling. So all those are the effect. So let's suppose we have balloon, and then if you warm a balloon, what happens? It may expand and then pop up, okay? It may break. Why? Because rising temperature changing the volume of air, and that increases the size of the volume of the balloon, and depending on how tight it is already, so if there is no more room for expansion, it's going to break, okay? We have seen those kind of phenomena. And there are some technological use, okay? So for example, a coffee pot, you enjoy your coffee most likely and like to keep, it hot all the time so that you can grab anytime you like. So for that reason, you have this kind of, like coffee pot that where you can set a temperature and temperature remains fixed. So here inside heating element of a coffee pot, for example, looks like this. So there is a heating coil that heats the, liquid or fluid, but there is this knob, and right next to knob, there are these two metallic strip. So what happens? One has a higher coefficient of expansion than the other. So right now, let's say your temperature. So what you can do is you can make this tighter so that it has less room for expansion and move. So it has, it has to expand a lot more to break or move away from each other. So here is the thing. So if you have, let's say, one expanding more than the other, and if you are putting something like that, both of these are expanding, but since one is expanding more, one gonna bend more than the other. So because of that, what happens is this joint separates once you heat up to a certain temperature. And when it breaks, for different temperature, it is calibrated and that is set in this knob. So if you turn that knob bit tighter, so that means to separate from each other, the force buildup, that tension force we talked about, that is stress force, is going to take longer. So it's going to take higher temperature. Okay, so that's why that gives you higher temperature. So you need to turn your knob a little bit more to get higher temperature. If you want lower temperature, leave it there. By doing this, you are pushing them together a bit more strongly, means it requires more stress to come apart. So what happens? This is what happens. Once it reaches to that temperature, they separate. So no connection means no current is flowing through this. So it acts as a switch, okay? And now let's suppose temperature goes a little bit down than the set temperature. By that time, what happens? They now come in contact. And then current starts flowing. And then again, as the temperature goes higher, what happens? It breaks. So that's how it acts as a switch to keep a constant temperature. So the device that keeps the temperature constant is called thermostat. And all the thermostats, they have some sort of this kind of mechanism to control a temperature, okay? So we build this because of the knowledge that things expand when there is rise in temperature and contract when the temperature falls, okay? So with that knowledge, we can invent this kind of technology. So now here is a question for you, and you have 1 minute and 30 seconds to answer. So let me warn you, many students make mistake in this question, so I want you to think a little bit harder here, okay? Oops, yes. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. Oh, what happened? Did I poll already? So is your clicker connected to my class, folks? You see that?
Yeah, I'm connected to your class. From on my screen, it says that the answer has been taken. The poll has stopped, but it hasn't gone past that. So you may wish to restart your iClicker stuff.
Oh, that's not good. So maybe running now gonna help? I don't know. What do you see in yours?
On ours, we see just a multiple choice question 1 detail. It says, you know, you cut out a big rectangular hole, your answer, da-da-da. But it doesn't say whether or not you got a correct answer.
Yeah, it looks like I need to restart everything. I mean, this clicker thingy here. So you may have to rejoin it, okay?
No problem. Yeah,
So,
it's kicked us out.
so okay, let's try one more time. I guess does it say new session? I don't know. So anyway, I'll take a look after the class or later. Okay. So I'm giving you 30 seconds to pull on this. 30 seconds, folks. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. now looks like we are in business. So A, C. So let's suppose I am thinking A as correct answer, just like many of you are thinking right now. Am I right or wrong, and why?
I thought it was A because the sheet metal, like both of the squares are made out of the same metal, so they would expand and, you know, contract at the same rate at the same temperature.
That makes sense. So Robert, want to say something there? Go ahead.
Sure. I think that I disagree. I think that instead, the other piece of metal is bigger than the whole, because this one piece of metal has 4 sides from which to expand on, but this sheet metal that we cut it out of has 8 sides to expand on. And I'm thinking to myself that that one of them is not going to match the other. That's why I said C.
So large, I mean the one with the hole, it can also expand inside.
That's correct. Because there's nothing stopping it from expanding on the inside. But if the sheet metal were already there, the fact that the sheet metal were there would stop it from expanding in the center. So everybody's got to expand out to the sides. But since there are no sides on this, there's nothing keeping it inwards, then it should just expand to the inward.
And that makes sense too. Now we have a problem. So that would mean plug would be smaller. No, plug is bigger than the hole. That would be plug is bigger than the hole. Just see. Hey, if I remember correctly, last time we had a response just like this. So how come I did not select any and it got selected? So anybody else want to chime in here? I picked B because it says the hole was caught when it was cold, and when it becomes warmer, it will expand so that the plug will be smaller. Okay, so did we separate that? So both were cold, and then when we are trying to fit, it's a summer day, probably. So change in temperature is going to be about the same, I think. Yeah, it's kind of, you know, both arguments makes equally sense here. For that, we need to actually, you know, take a look at the experimental evidence. So for example, let's suppose you are trying to fit a ring in your finger, right? Ring finger. So let's suppose you had a ring and then you took it out, and somehow because of the COVID thingy, you gain weight a little bit, right? So now you're trying to put a ring back in the finger and it's not fitting. One way to do it, probably you try lotion, soap, or something like that. If even that doesn't work, then another way to do it is to put that in a warm water for a while, hot water for a while, and then try that. Oh, hole in an ice cube. Oh, there is that. So ice cube probably is going to make even smaller. So that may not be a good idea, but if you put that in a water or hot water for a while, it may fit. So what happens is the hole also expands. So the molecular property, these molecules, they are also, like connected to each other, like in a string, that the bond thingy. So what's happening is everything is pushing it outward. And it turns out that when we have a situation like this that has a hole in it, it turns out it expands just outside rather than expanding inside. So in this case, a correct answer is A, but of course, C also makes sense before we actually do experiment and learn more about it. So I'm giving credit for all folks for this question here, even for D, which is not here. Okay, so everybody getting credit here. Okay, but A is the correct answer in this case. Okay, it turns out. Thank you everybody for participating in discussion, open mic or through the Zoom. Okay. So now let's talk about this. So we want to talk about how volume of the things change when temperature change and how the pressure change, and those depends on number of atoms and molecules or something like that. Okay. So in that case, we need to talk in terms of those number of molecules and so on. So to do that, what happens? Even for a very small amount of the substance, the number of molecules, they are very, very large, in very large numbers, okay? Because they are very tiny. So rather than talking in terms of those individual molecules and so on, what happens is we can come up with a certain amount, a certain number of the molecules, and then let's say bag them together. When we do that, that description is called mole. So mole is the amount of substance. It's kind of like a mass, okay? So how much substance is there that is related, that is kind of mole. So this mole and Avogadro's number, you are probably familiar with these numbers if you have already taken, I think, general chemistry. And remaining of this chapter gonna look very similar to that, okay? So let me try here to explain what those are, and hopefully you can relate those to what you have learned in chemistry as well and don't get confused, okay? So now let's suppose if we try to find mass of an let's say atom, how do we do it? You can look at periodic table, right? So periodic table, so some people have already done very hard work and listed those numbers in the form of periodic table. So this number here, so you may find, depending on what kind of periodic table you are looking at, there might be several information, but more general, you may find these two numbers here, which counts, like atomic number, it says 1, 2, 3, 4, 1 for hydrogen, 2 for helium, 3 for lithium, and so on, right? So 1, 2, 3. And then underneath that, there is this number, is called atomic mass. So that's the mass of an atom, but it's not in kilogram. It's in different unit, okay? We call that atomic mass unit. Now, if we have molecule, then what happens? Molecule is a combination of atoms. So in that case, if we want to find the mass of that molecule, for example, in this case, we are talking about a hydrogen molecule, because hydrogen gas, hydrogen mostly exists in gas form. So in that case, it's going to be a gas molecule. A gas molecule means two hydrogen atoms bonded together, right? So if we want to find molecule of a hydrogen, sorry, mass of a hydrogen molecule, then what we can do is we can just add the mass of two hydrogen atoms. One atom, another atom. So these two atoms make a molecule. So there is this bonding here, right? So if we want total mass of a molecule, then you can just add them. So it's going to be 1.08008, so on. And when you add, it becomes double. And the unit is atomic mass unit. Because these particles are so tiny, when we write that mass in kilogram, what happens is the number becomes so small, hard to work with. So what we do is we just remember conversion factor. Whenever needed, we can go back and forth. Otherwise, we can just say, okay, it is about 1 or 2, something like that. So 1 atomic mass unit, 10 to the power negative 27 kilogram, in the order of that. It's a very small number. So 1 hydrogen has mostly 1 proton and 1 electron. Mass of electron is negligible compared to proton. So basically, the mass of hydrogen atom is mass of a proton, essentially. Okay, so the unit, by saying close to 1, we are saying, okay, the unit we are using here, atomic mass unit, it is just about the size of 1 proton, let's say. But hydrogen have just proton, but other elements have proton and neutron. Proton and neutron, they have all the similar mass. They are not exactly same. So when we take average, what happens is, average of many of those, what happens is, that's why we're not getting nice number 1 here, okay? But we have slightly different number because we have neutrons and the protons in the nucleus, and that's what makes the mass of an atom, okay? So if we have just protons, probably our 1 atomic mass unit would be exactly, or let's say hydrogen of, mass of hydrogen, atomic mass of hydrogen would be exactly 1. So that's why there is this difference in number. So what we do is we take kind of average thingy. So for that, we go to the carbon. Carbon is most prevalent element in our nature, right? So because of that, what we do is we go for carbon, and we take carbon atom, and carbon atom with isotope number 12 means it has 12 protons and 12 neutrons, exactly equal, okay? So what we do is we take that element that has 12 protons and 12 neutrons, right? And then we also weigh 12 gram, exactly 12 gram of that carbon. And then we count, we go back and count how many number of atoms are there in 12 grams of carbon. Oh, a lot of them. If you try to count them, you need, of course, microscope to find out one atom versus another one. So if you directly count it, it's going to be very impractical. But yes, of course, there are indirect method of doing it. By doing it, people have figured out if you were to weigh 12 grams of carbon and count all the atoms, how many of you get? You get that many, okay? So we call that Avogadro number, okay? So, and we call that amount a mole for the carbon. So if we have whatever amount of mass we have in that many number of that corresponding atoms or molecules, that mass is 1 mole. So this number is fixed. So if you want to find mole of anything, what you do, you need to first look at whether that thing is just made up of atoms or it has molecule, it exists in molecular form, okay? So for example, here we talked about hydrogen. Hydrogen gas exists in molecular form. So if you need to find 1 mole of hydrogen gas, what you need to do? You need to count that many number of molecules of hydrogen now. And that's going to be 1 mole of hydrogen. But let's say if you have something like copper, iron that exists in the form of atom rather than molecules, what you do, you count that many number of atoms, and whatever mass you get, that's going to be 1 mole. So this is another way of expressing mass. But in this case, what is fixed is this number is fixed. And where did this number come from? By using or by weighing 12 grams of carbon atoms and counting the number of atoms in that 12 gram of carbon, okay? So why did we weigh 12 gram? Most likely it is because there are 6 protons and 6 neutrons in carbon, right? Carbon has atomic number 12, is that correct? Do I remember that correctly? Okay. So regular carbon, that's that. But of course, some carbon element, they have more neutrons inside than the proton. So that's a different isotope. So that's a different story. But anyway, so that's what we do. So now what happens? If the entities, for example, atoms or molecules are smaller, then 1 mole of that thing gonna be less than the other thing. So that you need to keep in mind, okay? So that's what 1 mole means, okay? And 1 mole comes from by counting certain number, that's the Avogadro number, of either atom or molecules. And it depends on the structure of that substance. So if it exists in atomic form, we count atoms to get 1 mole. If it exists in molecular form, then we count that many number of molecules. Okay. So now, if we know mass of a molecule or atom, and since we're going to be talking about gas, let's say these gases exist in molecular form rather than the atomic form. So that's why it's saying mass of a molecule is m. So if you multiply that mass of a molecule by total number of molecules in a mole, that's going to give you the mass of the mole, right? So that's how this Avogadro's number comes in handy. So since 1 mole has that many number of molecules, to find total mass, you need to add all of them together, okay? And adding that many is also equal to multiplying 1 by the numbers, okay? So now here is a question for you, okay? So go ahead, read and answer, and you have 2 minutes to answer this question. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got here. So mostly C. Nobody chose D. Okay. So we are talking about how do you find how much sulfur is there. So we want to find mass. So first we need to know if the sulfur exists in molecular form or the atomic form here. Yes, sulfur gas exists in molecular form, but here it's not sulfur gas, it's sulfur crystals. So they exist in atomic form here. So that means we don't need to double the sulfur. So we don't need to do S2 like H2. We don't need to do. We just need S. So what's the mass of one atom of sulfur? So for that we need to go here. Hey, that's not atomic mass. That's the atomic number. That's the atomic mass. So it is 32. So it is 32 for one atoms. Now, to find mole, it says 1 mole. So that means it has Na number of sulfur, Na number of atoms there. So Na times mass of one number. So yeah, it looks like C is the correct answer in terms of atomic mass number. Now, how about in kilogram then? So once we know that, we need to use conversion factor, right? Remember we had like 10 to the power in the order of -27 kilogram we wrote in the last slide. So we need to use that. So anyway, we can find that. So now let's talk more about gas. So it says ideal gas, ideal versus real gas. So the gas we find in our life is the real gas. For example, air, they are real, right? If you, let's say, put air in the balloon, actually you are pumping carbon dioxide there if you are using your mouth, right? So there is carbon dioxide in balloon. So those are real gases. And what happens? One molecule of gas interact with another. There is force between those molecules. And to do the analysis with that, what happens is it makes difficult. Math becomes difficult. Now, if we assume these molecules, when they are in gaseous form, they are kind of far from each other, and interaction between them is negligible, then things become a bit easier. Okay, so by doing that, what we are doing is we are idealizing it. Okay, so that's what the ideal gas means. So ideal gas means these gas molecules are far from each other. So how far is far enough? Did I write that? Probably not. So here, let's say there is one gas molecule and there is another gas molecule. So if the separation distance between them is larger than their size, then we can say, okay, the separation distance is large. And we can say, okay, you know, the density is not that large. Okay. So in that case, we can describe that gas as an ideal gas. And the physics we're going to be missing going to be not much. Okay. The physics is going to be still same. Property is still going to be about same. Not 100%. Maybe we're going to get a result within, let's say, 98% with, you know, without going through that difficult math. So that's why sometimes we make approximation while doing problem, okay? So when we make approximation, what happens? We avoid a lot of mathematical trouble, but in terms of result, the information, we get almost all information. Not all, I'm not saying we get all information, but almost all, okay? So that's what that is. So when we have the gas, ideal gas like that, and we try to, let's say, change pressure, volume, and temperature one by one. Remember in science, we do experiment controlling the variables. So when we do that, what we find is that if we keep volume constant and just change the temperature, what happens? Pressure changes proportionally. So if you double the temperature, pressure doubles. If you triple the temperature, pressure triples. But when we say temperature doubles, keep in mind, we are talking about temperature in Kelvin, not in Fahrenheit, not in Celsius. And remember, change is same in Celsius, in Kelvin, and in Kelvin. But temperature itself is not same. So you cannot just, you know, replace Celsius by Kelvin. You cannot. You need to do proper conversion using the formula I wrote. But of course, you can find those formula everywhere, including in the book. So what it means is temperature and pressure, they are directly proportional. And when we plot graph, we get a straight line graph for that kind of situation. And of course, this one shows us that if we were to extend that, it goes all, you know, directly down near the zero temperature. Okay, so here, temperature in Kelvin, 300, 200, so on. And by the way, 300 Kelvin is around room temperature, slightly more. Okay, so how much is 300 Kelvin? 300 Kelvin is your warm room temperature, let's say. Okay, when your temperature is warm, that's around 300 Kelvin. Just for, you know, some idea. Okay, so if you keep on lowering it down, what happens? It goes towards this down here, and that temperature we call 0 Kelvin. Okay, so anyway, so that's what we use as a SI system of unit, because the pressure goes 0 at that temperature. So basically, everything freezes in place at 0 Kelvin. The gas molecules, they are not wandering around anymore at that temperature. Okay, they are not exerting pressure. Remember what pressure means? Pressure means when these gas molecules are hitting on the side, right, and bouncing back, that's what the pressure is. If they are not doing that and just sitting still, frozen, that means no pressure there. So 0 pressure, that's where it comes from. So now that's one observation. So now let's take a look. What happens to the volume if we keep pressure constant, but change the temperature? Oh, looks like in this case, we are just keeping temperature constant, okay? And what we find is, so we are just looking at the variation in pressure, okay? So volume and pressure, they are inverse, and probably you may have noticed, right? When you squeeze something, make volume smaller, it becomes tighter and pressure becomes larger. So for example, if you put some air in a balloon and then you start, making the volume smaller by moving your fingers down there, then what happens? It becomes tighter and tighter. And if you keep doing that, it may even break. So pressure and volume, they are inversely related. You squeeze something, it becomes smaller if it is squeezable. And gases, they are compressible, means you can change that, okay? So on the chat, I see 300 is equal to 80.33 degrees. Is that Fahrenheit or Celsius? So our room temperature is around, when we put 75 Fahrenheit, it's comfortable, right? So 80 is a bit warmer room. So that's what I was talking about. Yes, thank you for doing that calculation, but it is in terms of Fahrenheit though, Mr. Torian. In terms of Celsius, I think it turns out around 27 or something like that, okay? Okay, so now another thing is n number of gas molecules. So when we put more gas in tire, what happens? Pressure becomes larger, right? So we know that. So they are inversely related. So we can just combine them together and can write the ideal gas equation. And by the way, each of these observations, they have their own name because Boyles, Charles, they individually did this experiment. But now we can combine all of them and then just write one equation and we can get all information from one, okay? So, yes. So this proportionality sign, to remove proportionality sign or replace that by equal sign, there is, there is a technique in mathematics we call, we use a proportionality constant, and that depends on different situation. So in this case, that turns out to be, we are keeping that as a K. And K turns out to be that number, and this is another standard constant. Remember, we had Avogadro's constant, and now we have Boltzmann constant. Avogadro's constant, it was a very large number, and this Boltzmann constant, it is very small number, okay? Okay, so that's how we can write it, but the gas laws can be written in different form. So we'll talk about that, and it looks like we already passed the break time, so let's take break. Sorry about that, we went a little bit over that. So after we come back, we're gonna write different form of this gas laws and then learn how to use it, okay? Okay, folks, I'm back and welcome back. Okay, so now, just like I was saying, this gas law you can see in different form, okay? So for example, one is to, first let's try to write this n in terms of Avogadro's number, okay? So this is total number of molecules, and we know in 1 mole there are a number of molecules. So if we have n number of moles, total number of molecules is going to be number of moles times the number of this number in 1 mole, right? So for example, it's like saying, let's suppose one package of apple has 10 apples, right? Now, how many apples are there if we have 5 packages? So what do? We just multiply 5 by number of apples in each package. So 5 times 10, 50. Same idea here. Number of package, N, and number of apples in each package, NA. So that gives you total number. So here package being moles and NA being the Avogadro's number, which is number of atoms or molecules in 1 mole of substance. Okay, so now when we put that, what happens is we have 2 constants here. Na and K, both of them are constants. And product of those constants gonna be a constant, right? So we can replace 2 constants by just single constant. And that's where this R comes in. And remember, this Na and K, they don't depend on what gas it is. So that's why the R also does not depend on what gas it is. So it is called universal gas constant. So it's the product of this number and the Na, Avogadro's number. That's what that is. Both of them are constant. So when we multiply it, what we find? We find this as a number. Keep in mind though, here we are writing this unit in terms of joule. So see, this number had a joule here, so we are keeping in terms of that. So depending on what unit you are using, if you are not using a standard SI unit, then in that case, the value of R may be different. For example, let's say if you used pressure as an atmosphere rather than using Newton over a square meter or Pascal. So rather than using this, if you use Pascal, sorry, not Pascal, but atmosphere, right, for the pressure. And similarly for the volume, remember, SI unit of volume is meter cubed or cube meter. But if you use, let's say, liter for the volume, and there are nearly 1,000 liters in each cubic meter. Then what happens? That number becomes different here. So probably you may have used value of R as this in chemistry, if you remember from the chemistry class. So when you are given value of R or when you are using value of R, make sure you are using the one with the correct unit, okay? So in physics, we use cubic meter for volume, and let's see, the Newton over a square meter for the pressure. What happens? We get this number. And by the way, just in case, remember this joule is coming from this. Product of pressure and volume is work done. Probably you remember from the fluid dynamics last chapter, we had their work done calculated while calculating the Bernoulli's equation. That had a product of pressure and volume for the work done. So when we multiply pressure and volume, we get work done means the unit gonna be unit of work done, which is joule. So that's where this thing is coming from. So anyway, so you can write this gas law in different form depending on your need and what is given, okay? So it comes in a different form. And this is the most standard one, okay? Where N is the number of moles and R is universal gas constant that comes from the product of Na and K. Okay, so now, so we can write this, you know, for different situation, we can write it slightly differently. We know R is constant, but in a situation when N is also constant, number of moles or mass constant. So for example, let's suppose you have a gas inside balloon or container, right? So in that case, what happens? If the gas is not getting out from the container or not getting in the container, that means number of molecules remain same, mass remains same. If that's the case, then N and R both going to be constant. So we can write that equation something like this. So I'm bringing this T down there. PV over T is N times R, constant. So in that situation, when it is in closed container, that means N is not changing. And in that case, this ratio becomes constant. So that means we can write that as something like this. And probably you may have seen and used this equation in this form, okay? So product of pressure, volume, and temperature at one temperature, that is equal to the products again at another temperature. So that's what it is saying. Now let's suppose if your container such a way that its volume does not change. For example, a rigid container, it has a rigid valve, so the gas cannot push and make the volume larger or smaller. In that case, volume becomes fixed. When volume is fixed, that means you can write this equation as just P1 over T1 is equal to P2 over T2. So depending on situation, you can write this differently. Here is one example. So let's suppose we are talking about air in a bike, tire, okay? So tire of a bike, volume remains approximately same, okay? It may change a little bit when temperature change a lot, but let's say it remains about same, okay? And that is given, and it's not saying it changes, okay? So let's keep it that way. Now pressure is that much, it's in Pascal. Pascal is Newton per square meter. That's what we are using. We are not using that pound per square inch. We are not using PSI here. Rather, we are using standard, and that's what you should be using, okay? And temperature is in Celsius. Oh, there we have to be careful. We need to convert that in Kelvin. Remember, all gas equation, they are written in Kelvin. And now let's suppose temperature changes, then how does the pressure change? So when temperature changes, pressure increases, we know that. But by how much? It's not done here, let's do it, right? So volume, B1, B2, it's same. That's what it means, right? And pressure at one temperature is 7.0 times 10 to the power 5 Pascal. And that temperature is 18, this is Celsius. So to convert Celsius into Kelvin, we need to add 273 and it becomes Kelvin. Okay, we need to work on that. Now, what is another temperature, which is 28. So when temperature in, let's see, when temperature in Fahrenheit, let's say doubles, temperature in Kelvin does not double. It is different. So you need to do proper conversion for the temperatures, okay? Keep that in mind. So that's that. So now the question is, what is pressure at this temperature? So using that gas equation, P2, V2, P1, V1, we have temperature as well. Oops, supposed to be T2, T1, right? So this equation, so volume is constant. They are same means this and that same cancels, right? And what are we looking for? P2. So P2, so bring this T2 over there, cross multiplication, other side. So it's going to be P1, T2 over T1. Okay, and P1 is given, so everything is given now. Oh, we need these numbers here, right? So T2 goes on the top and T1 goes down here, and you calculate that. And just for an experiment, what you can do is try calculating without converting temperature, and you'll get different number, of course, okay? Without converting temperature, that's going to be different. So when using gas equation, you always need to convert temperature in Kelvin. Otherwise, whatever you calculate, not going to be correct. Your answer should be based on Kelvin, not in other temperatures. Okay, so if you try to guess answer based, without thinking about temperature being in Kelvin, then your answer not going to be correct. So let's keep that in mind. Okay, so pressure. So pressure, volume, and temperature, that relationship we derived, we just wrote that down based on citing an experiment. Let's say if you do this, this is what we see, so let's write it down, right? But here we are deriving formula for pressure from very first principle using Newton's law. Remember, force is rate of change of momentum. We know that, right? So we learned that in momentum chapter. So that's Newton's second law, written slightly differently. Yes, of course, famous one is m times a, but if you write definition of a, you get there, okay? Now, what is pressure? Pressure is just force divided by area. That's what the pressure is, okay? So in this case, the final and initial velocities, let's say, are gonna be the velocity with which it is arriving and velocity with which it gets bounced back after hitting the wall. So that's how the momentum changes. It's not because mass is changing, but it's because velocity is changing. And for ideal gas, what happens is the value of velocity does not change from the collision much. Okay, it remains same, only the direction changes. So for convenient, what we can do is this container is cubicle 1, and we just look at the motion in one direction, okay, first. So in this case, change in momentum. So for example, final velocity, let's say this is positive bx, and initial is negative. And negative times negative makes it positive. So change is gonna be positive here, and that's what you see, okay? So here, the delta t was there, right? It came from the force, and a, length is square. So this being cube, length is square. For the area, we need just square of the length. So if we are talking about this area where these gas molecules are hitting, that area there, and then this area gonna be this length times this length. And since we are assuming this as a cube, this is gonna be square, so that's why we can write L is square, okay? So anyway, so that's how we get the pressure. So even if you don't understand what we are doing here, you're gonna be fine, but later you need to understand how to interpret and understand what the result means, okay? So that's what we're gonna be doing. But let's make this a little bit, better here. So time and length, they are related, right? And so time interval means it comes, let's say it goes there and travels L length and comes back. So that means it travels 2 times L length during that time interval with the speed Vx, right? So Vx, this distance and time, they are related. Vx is 2L over delta T. So if we like, we can get rid of this delta T by writing something like this, delta T as 2L over Vx. So we can do that. Okay, so delta T is there. And that's what we are doing. Once we plug that delta T, which is in denominator, what's gonna happen? V gonna go on the top here, and L gonna multiply with this, and 2 gonna cancel with that 2, giving us this. And L squared times L becomes L cubed, which is the volume of the container. And that's nice because now we don't need to worry about whether it's a cube or not. Okay, as long as we know volume, we should be fine. Okay, so that's the pressure, but it's because of the motion in EX direction. But these gas molecules are randomly moving, so that means the chance of going in X, Y, and Z direction equal. So that means there are going to be contribution to the pressure coming from all three directions. So what we can do is we can combine from all three directions, okay, X, Y, and Z, and this is for one mass molecule. If there are n number of molecules, then we can multiply n, and it's going to give you the total pressure. So now for Px, we can write this. For Py, we can just replace X by Y, and so on. Okay, so we can do that. And this is like a, you know, like 3 velocities being added. So if we have bx squared, by squared, and then we can write that as a b squared, right? Like a Pythagorean theorem. Here it's a 3 dimension, so it's kind of same idea. But on average, what happens is it becomes 1/3 of the square of that. Now, here, what I'm doing is I'm multiplying by 2 and dividing by 2. By doing this, I'm getting this half mv squared. And we know that's going to be the kinetic energy of the molecule of that gas. So I can write that as something like this. Okay. So pressure, volume, and kinetic energy, they are related. So if kinetic energy is larger, that means it's moving faster, means pressure gonna be larger. Kind of makes sense, isn't it? Okay. And if we were to use this PV is equal to nRT equation from last slide, remember from the gas law, what we can do is we can get rid of this number of molecules and things become even simpler. So let's do that. So in this case, I use the original one with the total number because I want to cancel that rather than in terms of moles. I'm not using moles, rather I'm using the very first equation I wrote. So that way this n and n cancels, giving me this nice equation. So it tells me the kinetic energy simply depends on temperature. So that's where the definition of temperature comes from. What is temperature? Temperature is the average kinetic energy of gas molecules. So higher temperature means kinetic energy is higher. That means they are moving faster on average. Okay, so that's what it means. So that's the definition of temperature. So what is the temperature of a gas or temperature of anything? That's the average kinetic energy of all the molecules or the atoms in that thingy. Okay, so what happens when you heat something? Things starts oscillating faster, velocity becomes larger. So that's what it means. Kinetic energy and temperature, they are directly related. K is constant, 3/2, of course that's constant too, right? So this is one main formula, and whenever needed we can always go back and write this K average as this. Remember that came from there. So that's the nice thing about it. So let's look at one example here. It says estimate the average speed of nitrogen gas molecule in room temperature. So room temperature is 296, it is saying in terms of Kelvin. Okay. If it is warm room temperature, it is around 300 Kelvin, I was saying. Okay. So it's given 296 and it's given in Kelvin. That's nice. If it wasn't given in Kelvin, you need to convert that. So now, in this case, it says how fast it is moving, nitrogen molecule. So see, you have air inside this room, and air is mostly made up of carbon dioxide, oxygen, and nitrogen, right? 3. Others, they are just traces. So now, if you want to find how fast the nitrogen molecule is moving in a room temperature, so how fast it moves simply depends on room temperature, see? So by knowing just the temperature, you can estimate the average temperature, average speed of the nitrogen molecules. And you can do the same thing for the carbon dioxide. You can do the same thing for the oxygen. Isn't that neat? You cannot even see them, but you can tell how fast they are moving on average. Yes, some molecules may be moving a bit slower than the others, but on average, that's how fast they are moving. Okay, so since it's talking about mass, the speed, and the speed is in the kinetic energy, we need to go back and write it in terms of mass and velocity, right? So now we want speed. So let's solve this one for speed. So this 2 and 2, we can cancel that. And then move this mass on this side and take the square root, okay? And that's what I'm doing here. So that's the average speed. Now we are ready to plug in the temperature that is given. And we also need mass. And remember, mass needs to be in kilogram. So for that, you can always look at the periodic table. So nitrogen is here. So mass comes from here. And since we are talking about nitrogen gas, that means we are talking about N2, not just N, right? So that means it's going to be 2 times 14, okay? For the mass, that's what we need to write. Oh, there is that. And that's going to be in atomic mass unit. And to convert that in kilogram, you need this conversion factor, okay? So after plugging in all the constants, I get this. And if I calculate that, hey, 513 meters per second. Oh, that's a very fast speed. In terms of meter per second, if you are running, maybe you are going between 5 and 15 meters per second, something like that, okay? 513, really fast. So these gas molecules are moving really, really fast, faster than the speed of the bullet that comes out from, let's say, some rifle, long range rifle. That's how fast they are moving. Fortunately, they have really small mass. Because of that, they are not killing us, okay? Otherwise, we all be dead if those were larger mass. But of course, if they were larger mass, they wouldn't be moving that fast either. So anyway, we would be fine, I think, okay? So that's how we use this formula. So now let's take a close look at this formula here. So it says when temperature increases, speed increases. But this being inside the square root, for example, when temperature doubles, when T goes to 2 times T, the speed does not double. To double the speed, what has to happen? The temperature has to go from T to 4 times T. It has to be quadruple. When temperature quadruples, the speed doubles, everything else remaining same. Now, if you want, let's say, average speed of oxygen, what do you do? See, for the same room temperature, you can keep that same thing. What changes? Just mass. And oxygen is O2. And we know Oxygen has mass around 16. So it's going to be 16 times 2 U, but in terms of kilogram, it's going to be 1.66 times 10 to the power negative 27 kilogram. Okay, so now you can plug that in there. So which one has a larger mass, oxygen molecule or nitrogen molecule? You can type that on chat if you do not want to speak. Which one has a larger mass, oxygen molecule or nitrogen molecule? Mass we are talking about, not the speed, right? So nitrogen has a 14 times 2. Oxygen has 16 times 2. Which one is larger? Oxygen is larger. Since mass of the oxygen is larger, is it moving slower or faster than nitrogen? Larger mass makes the speed slower, right? So that's how you need to look at this formula and be able to answer question. There may be a question like this here. Okay. Which one of them is moving slowest? Okay. Hey, directly related. So 1 minute and 30 seconds, folks. Thirty more seconds. Looks like I gave too much time here. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So again, we need to write this in terms of half mv squared, right? And just like we did in last slide, it turns out to be 3 kT over m. Mass and speed inversely related. That means the heaviest one is moving slowest. Now here we don't have carbon dioxide. So for that we need to remember carbon dioxide is CO2, right? So now its mass is going to be combination of all three. So carbon 12. Yeah, you don't need to calculate mass because it's not asking you to find the speed. But just in case, if you are asked, you can do carbon is 12. And then there are 2 oxygen means 2 times 16. Right? Is that 48? Oh, no. 44? Yeah, looks like that's 44. So the oxygen has 32 and nitrogen has 28. So 28, 32, 44. So this is the heaviest one. So heaviest moves slowest. So that means, looks like it's gonna be the carbon dioxide. Did I poll on this? Looks like I did, and most of you figured out just fine, looks like. So you are becoming expert on this. So, yeah, so there are more on this section. For example, heat capacity, that is another important aspect. And then laws of thermodynamics, right? But I'm going to be skipping those chapters and moving to the oscillations, pendulum, and how do we analyze the motion, oscillating object? How do we describe that using concept of position, velocity, and also using the concept of energy. So that's what we're going to be doing, okay, for the another class. So gas laws and kinetic theory of gas, so that's what we are doing from this chapter here. And we're going to move to the oscillations. So I'm skipping some chapters here in between. Some of you who took chemistry, probably you're already familiar with those materials and you already know it, just like for some of you, these were all familiar materials, I'm guessing, okay? So for that reason, what I'm doing is, even if you haven't taken chemistry, I'm pretty sure you're going to be taking chemistry over there, you're going to cover these materials, but you're not going to go and learn about oscillations, pendulums in any other class. So that's where I want to go, okay? So that's where we're going to be moving next. I hope I set up my pre-lectures correctly. For the next, I'm hoping it's oscillation, is that right? So pre-lecture exercise was about the oscillation, is that right? Okay, anyway, folks, so it looks like this, I'm done for this chapter. If you have any question, feel free to ask. Otherwise, we can leave it here today, and I'll see you guys on Wednesday. Okay.
Thank you, Professor.
Thank you.
Thank you.
Thank you.
Thank you.
Professor, I had a question for you. I was wondering if you had any idea what day our final was going to be. I saw some teachers posting dates, and I didn't know if you knew yet.
Yeah, I do.
Oh.
It's Monday of the final week.
Okay, so that is the 7th. Finals is 7th to the 12th, I think.
If it is 7th, yes. On the final week, yes, it is. Yeah.
All right, cool. Yeah, I'll double check the date, but the Monday of finals week. Got it.
Yeah, that's all I know for now, but I need to double check, and I'll write email to the class. Okay.
Cool. Yeah, I figured. I appreciate you letting me know. Thank you.
Okay.
I also had a quick question, if that's cool.